In the beginning of his book, A Brief History of Time, Stephen Hawking told the story of a little old lady who rejected the theory of a Big Bang. Somebody asked her for what her theory was, and she responded that the Earth sits on top of a plate which sits on the back of a turtle. Somebody asked her what's below the turtle, and she answered, after that, it's turtles all the way down. There were 2 points to Hawking's story. One was that the theory of a Big Bang, like any other theory, could be completely wrong. The second was that there is a basic alternative to the Big Bang. That alternative is a universe that has no beginning and has no end. It repeats itself indefinitely and works the same everywhere at every time. Galaxies are among the largest things that we know about, and atoms are among the smallest. What if galaxies share atomic physics? And what if it's atoms all the way down? Astronomers have discovered that galaxies form large-scale structures that look like suds in a kitchen sink. Galaxies form walls which surround massive voids. Explaining why these structures exist poses serious challenges for current models of cosmology. But if galaxies shared the tendency of atoms to form repeating structures such as a crystalline lattice, then this is exactly the kind of thing that we would expect to see. Since the last century, astronomers have known that most galaxies in the universe contain large spirals. Current models of cosmology offer no fundamental explanation for the striking and obvious feature. But if galaxies share atomic physics, then there might be one very simple explanation for spirals. According to long-forgotten theory of atomic structure, atoms may have spirals too. In 1867, Lord Kelvin proposed one of the first modern models for the atom. Kelvin knew that atoms transmit electricity, which has fluid-like properties. But atoms themselves are rigid or frozen structures. Figuring out what atoms look like is like solving a riddle. What moves but stays in one place? Kelvin's answer was a vortex. If true, this would fundamentally explain why we see large spirals in galaxies. Because what we are seeing is what atoms look like. Signs of a shared vortex structure. The long-forgotten vortex model has a number of advantages. First of all, it could explain one of the most noticeable features of atoms, gravity. A vortex sucks in everything around it. But the most intriguing thing about the vortex model is something that Lord Kelvin did not know, that it could explain why there are giant spirals, loops, and vortex-like jets originating at the center of galaxies in the known universe, including our own. When viewed in the radio spectrum, galaxies exhibit remarkable vortex-like structures and characteristics including tornado-like jets and lobes that originate from their centers. The center of our own galaxy, the Milky Way, shows large fluid-like arcs near its center. Numerous other galaxies and related objects like microquasars also show large fluid-like loops or corkscrews originating from their centers in the radio spectrum. But if galaxies are like atoms, then what are stars? Stars occupy the space in and around galaxies. They have different colors, with blue stars being larger and red stars being smaller. If galaxies are like atoms, then stars may be light. If stars are light, then light itself must also be composed of a stream of little stars traveling in between atoms. That would mean that light is not wave-like. Rather, it is composed of small bodies that have mass, much like Isaac Newton originally thought. This leads us to the crucial flaw in the Big Bang model of the universe. The flaw is the theory that light Doppler shifts. The Big Bang model says that the redshift in galactic spectra is caused by galaxies moving away from us. Because the atomic spectra in nearly every galaxy exhibits a redshift, the theory proposes that the universe is expanding away from us. But the redshift that we see in galaxies can be explained by a simpler and more straightforward theory, namely that light simply redshifts as it travels long distances. If light actually Doppler shifts, then we should be able to detect and measure that Doppler shift in a controlled experiment. The required velocities are very high, as well as the required spectral resolution, but there is a workable experiment. A high-resolution spectrometer could conduct a number of controlled observations of the planet Mercury, whose orbit shows the most highly variable radial velocity of any planet with respect to the Earth. If light Doppler shifts, then there should be a detectable shift in Mercury's average spectra at those times when its absolute radial velocity is the highest, corresponding to a Doppler shift. If light does not Doppler shift, then Mercury's spectra will exhibit no Doppler shift. Some examples of atomic behavior in galaxies may not be so obvious. For example, objects called dwarf galaxies and microquasars have been identified inside the Milky Way and other large galaxies. These objects display many properties of galaxies. Atoms contain neutrons, which are essentially small atoms. It may be that dwarf galaxies and microquasars correspond to neutrons. Radio imaging of the nearest galaxy group, the M81 group, reveals fluid-like streams connecting the larger galaxies. If galaxies share atomic physics, then what we may be seeing here is a form of molecular bonding between galaxies. Notably, our own galaxy group, the Milky Way group, contains 3 large galaxies in a similar triangular alignment. Stars across the known universe are mostly the same 2 approximate colors. This is referred to as a bimodal distribution of star formation. The color of a star may correspond to its color of light. And in the same way that atoms primarily produce certain colors of light, known as atomic spectra, individual galaxies may also primarily produce only certain colors of stars. Atoms generate light. If galaxies share atomic physics and stars are light, then galaxies must also generate stars. Galaxies are surrounded by objects called globular clusters, which contain very tight concentrations of stars that are mostly the same color. This may be where stars are generated in a galaxy. Atoms absorb light, and so if galaxies share atomic physics, then they must also absorb stars. Stars disappear in the black hole located at the galaxy's center. This may be where a galaxy absorbs them. When atoms absorb light or other radiation, they generate electric current, the photoelectric effect. And when atoms generate radiation, they lose electric current. These somewhat obscure processes in the atom could be the most important physical phenomena in the entire universe, because when they occur in a galaxy, they are the mechanism by which atoms are created and destroyed, both the origin and the end of all matter. When the galaxy produces a star, the galaxy must be converting an electric current of some kind into stars, and when the galaxy absorbs stars, it must be generating this electric current. But what is the galaxy's electric current? In other words, what does the galaxy use to create matter or atoms? And what does the galaxy generate when it absorbs or destroys them? In an atoms all the way down universe, there can be only one answer. After all, it's atoms all the way down. There must also be atoms in the atom. These are what would make up the atom's little stars or light. They are the theoretical equivalent of photons. In other words, the quanta that compose light. We could call them subatoms. By the same token, there must also be objects so large that when compared to them, galaxies are like the size of atoms. We could call these supergalaxies. As the next available thing in an atoms all the way down universe, subatoms must compose the galaxy's electric current. The galaxy generates atoms and stars from an electric current of photons. And when the galaxy absorbs or destroys stars, it generates photons. This is how the universe must fundamentally work. It is constantly creating and destroying itself at every dimension. The idea that galaxies have an electric current composed of photons or subatoms could fundamentally explain why large vortex-like galactic structures show up mainly in the radio spectrum. Remember that in the vortex atomic model, the atom is a vortex made up of a fluid-like electric current. Applying this model to the galaxy may be a vortex made up of a fluid-like current of photons or subatoms. These photons are special because they do not emit from atoms, rather, they emit from the galaxy itself. This may be why the most vortex-like features of galaxies show up as stray radiation. This radiation was flowing through and part of the galaxy itself. It therefore reveals an image of the actual galaxy atom. The visible matter that we see in galaxies, atoms and stars, are really just the galaxy's radiation. So when we look at the stars in a galaxy, it's like looking at a photograph of the light emitting from an atom. The electric current in the galaxy, i.e. its underlying structure, is not visible to the naked eye. For that, we need to view the galaxy in the radio spectrum. The difference in scale between a galaxy and a photon must be such that at the level of a galaxy, photons behave much like a fluid. They are present nearly everywhere, but with a measurable general direction and pressure. Galaxies may create such an intense pressure on photons as they flow through the galaxy that the photons merge until they actually reach the size of an atom. Conversely, the galaxy may exert such pressure on atoms at the center of the galaxy that the atoms split down into photons. Understanding exactly how galaxies actually create and destroy atoms is no doubt one of the most important final frontiers in all science.